Hey everyone, Mr. Fransky here. Today we're going to be talking about improper integrals. This is the last section of Chapter 8, so let's jump into it and see what happens. So we're going to start with kind of a little discovery learning here. So we try to find out where we're going with this. So we're going to evaluate the following for both f of x equals 1 over x squared and f of x equals e to the negative x. So if you want to pause this, these are all integrals you should be able to do and evaluate using antiderivatives, and we can try them together after. All right, so to try these out, the first one we got 1 over x squared. An antiderivative for this would be good. So that's x to the negative 2. So the antiderivative, remember we add 1 and divide by the same thing. So that's going to be x to the negative 1 over negative 1, which is the same as negative 1 over x. And e to the negative x, antiderivative of that, if we take the derivative, it'll be e to the negative x, but there'll be a negative in front. So to counter that negative, we put a negative to the front. So negative e to the negative x, okay? So we have our two antiderivatives here. Then we do these in different colors. Let's do 1 over x squared in purple, and then we'll do the e to the negative x in different color. So if we do the antiderivative here, it'll be negative 1 over x, evaluated from 1 to 10. So that is negative 1/10 minus negative 1 over 1, which is negative 1/10 plus 1. Okay, so 1 minus 1/10 is what, 9/10? All right, the next one, if we do it from 1 to 1,000, so negative 1 over x, 1 to 1,000, let's see, that's going to be negative 1 over 1,000 plus 1 again. Okay, so that's what, 999 over 1,000? So this last one, you might be able to see where we're going with this, it's going to be negative 1 over 1,000,000 plus 1, which is 999,999 over 1,000,000, which is essentially equal to 1. Right, it's very, very close to 1. Right, this was be 9/10. This was 999 over 1,000. And this one was 999,999 over 1,000,000, which is pretty darn close to 1, right? So let's try with e to the x, e to the negative x, excuse me. Let's change to a different color here, about blue. So if we do negative e to the negative x, from 1 to 10, that's going to be negative e to the negative 10 minus a negative, so plus e to the negative 1. So e to the negative 10, really small number, right? Negative 1 over e to the 10th. And then this would be plus 1 over e. Next up, if we go negative e to the negative x from 1 to 1,000, we're going to have negative e to the negative 1,000. Plus e to the negative 1, which is 1 over e. Then the last one will have negative e to the negative 1,000,000 plus 1 over e. So this is essentially 0, so this is pretty much 1 over e. So the question here is, where are we going with this? Well, would it be possible to integrate from 1 to infinity? Well, in these cases, I think we could, right? Because the bigger this number gets, the smaller this part of the integral gets for e and this part for 1 over x squared. So the smaller this gets, it gets closer and closer to 0. The point is, no matter how high you integrate, this will never go over 1, and this one will never go over 1 over e. So it seems like there's kind of a limit here, right? And these limits are what are going to be important and are going to drive our discussion today. So 3 important limits that we want to talk about. Get back to purple here maybe. So the first one is if f of x is continuous on bracket a infinity, then we can integrate from a to infinity f of x dx. And all we do is we do the limit as b approaches infinity, integral from a to b of f of x dx. So what you do is you take the antiderivative, so like for the 1 over x squared, you would do negative 1 over x, and you evaluate it from a to b, and then you would take the limit as b approaches infinity. Now that limit may not exist, it may converge or it may diverge. That's the way we talk about these, is we could say they converge or they diverge. They converge to a limit, or they diverge, they do not converge to a limit. So it's possible that limit won't exist, right? But in this case, if you do that, so like I think we went from 1, right? So we went from 1 to infinity, so I'm going to do it from 1 to b. So you would have negative 1 over b plus 1 over 1. As b goes to infinity, this guy turns into 0, so it ends up being 1. So we say, it's kind of weird, right? Because 1 over x looks like this. So what they're saying there is that if you integrate from 1 all the way off to infinity, so you find out all that area, it will never go above 1, so we just say it's the limit. It's the value that it will never go over, because you can get as close to 1 as you want, so we just say, okay, let's just assume that the area underneath there is 1. So the next one, if f of x is continuous, Oops, too many buttons. On negative infinity up to b included. Then we can integrate the other way. We can integrate from negative infinity to b, f of x dx would be the limit as a approaches negative infinity, integral from a to b, f of x dx. So you can do one side or the other side, you can do both sides. So the third one, if f of x is continuous on negative infinity all the way up to infinity, so on its entire domain, then we can integrate from negative infinity to positive infinity of f of x dx. Now, this one's kind of weird, because what you have to do is you have to split it up into two pieces. You have to split it up from negative infinity to any c value you want, f of x dx, and then we add to it the integral from c to infinity, f of x dx. So c, a good c is 0. So a good c value would be 0. You could use 1. You could use any number you want, right? Because you're integrating from negative infinity to infinity. So the ones like this that usually work, like the bell curve, right? You might remember the bell curve from stats. The area under there should be 1, right? And that's the integral from negative infinity to infinity. And your teacher probably had to do some convincing to convince you that even though it goes forever, the area will never go above 1, so we just assume that it's 1. So in this case, you could integrate from negative infinity to 0, and then from 0 to infinity. So all of these can converge or diverge. So converge would mean that these limits would exist, and diverge would mean that these limits do not exist. So for this last one, you would have to do two limits, right? One for the left side, one for the right side, to be able to find out if that limit converges. So if at any point in this process you get a limit that does not exist, that means you have a divergent integral. Cool. Let's try some. So the question is, are they convergent or divergent? So this one, we're just going to do it straight from the definition. So we're going to do the limit as a approaches negative infinity, integral from a to 0, e to the x dx. So that would be the limit as a approaches negative infinity. Antiderivative of e to the x is just e to the x from a to 0. So now we plug them in. So we have the limit as a approaches negative infinity, e to the 0 minus e to the a. E to the 0 is 1, so this is the limit as a approaches negative infinity of 1 minus e to the a. Now, as a approaches negative infinity, if you think about e to the x looks like this. As a approaches negative infinity, e to the x approaches 0. So this is equal to 1. How crazy is that? Negative infinity to 0. This area is equal to 1. E is so cool. I love it. Cool. Let's try another one. So negative infinity to infinity. Now you probably can guess on this, since e to the x goes up forever. Negative infinity to 0 might work, or negative infinity to 1, or any value you want, right? But if you keep going to the right, eventually this is going to go off to infinity. I don't think it's going to work. But we got to break it up. So I'm going to break it up at 0. So we're going to integral from negative infinity to 0, e to the x dx, plus the integral from 0 to infinity, e to the x dx. Now, the left side we already did, right? But I'm going to write it out anyway. So it's the limit as a approaches negative infinity, integral from a to 0, e to the x dx, plus the limit as b approaches infinity, integral from 0 to b, e to the x dx. So you have to do two separate limits. You can't do it all at once. And if either side diverges, or the limit does not exist, then that's going to be a divergent integral. Okay, improper, they're called improper integrals because you have infinities on one side or the other. That's why they're called improper. So we have the limit as a approaches negative infinity, e to the x, that's the antiderivative, right, from a to 0, plus the limit as b approaches infinity, e to the x from 0 to b. So this is e to the 0 minus e to the a. As a approaches negative infinity, this turns into 0. So we should have e to the 0, which is 1. This part, though, we have e to the b minus e to the 0. Now, e to the 0 is 1, but e to the b increases without bound. That goes to infinity, so this is divergent. Or we say the integral diverges. Cool. Next slide. Come on, baby. There we go. All right, now we're going to get back to some of our fun integral techniques. So we have integral here from 0 to infinity, so we're going to do the limit as b approaches infinity, integral 0 to b, 2 over x squared plus 4x plus 3. And I remember how to integrate this. Looks like that bottom is factorable, so I think we're going to have to use partial fraction decomposition. All right, let's jump in. Limit as b approaches infinity. I'm going to pull the 2 out to the front. We'll figure that out later. Integral 0 to b, let's factor. So we have 1 over x squared plus 4x plus 3. Looks like x plus 3, x plus 1. dx. Okay. So now we can set up our partial fraction decomposition. So we have, this would be equal to a over x plus 3 plus b over x plus 1. Oh, come on. Okay, so if we multiply both sides by the entire denominator, we're going to have 1 is equal to a times x plus 1 plus b times x plus 3. Convenient values for x. Let's try x equals negative 1. So we have 1 is equal to what? Negative 2b? No. 2b. 2b or not 2b? Okay. So b is 1/2. And if x is negative 3, then we have 1 is equal to negative 2a. So a is negative 1/2. So we have limit as b approaches infinity. Integral from, sorry, 2 in the front, 0 to b of a is negative 1/2 over x plus 3 plus 1/2 over x plus 1. Now, thank goodness we have no chain issues, so we can just do a natural log here. So we have 2 limit as b approaches infinity of negative 1/2 ln absolute x plus 3 plus 1/2 ln absolute x plus 1. Now, if you plug in, that is from 0 to b. If you plug in b here, you're going to have an infinity here and infinity here. So we have an infinity minus infinity situation. So we're going to have to somehow combine these. Well, we can pull the 1/2s out. It's going to cancel with the 2. Thank goodness. Okay, so you have ln absolute x plus 1 minus ln absolute x plus 3. Everything is positive here because anything adding 1 or 3 is going to make it positive, starting at 0 all the way to b, so we don't have to worry about the absolute values. So this is the limit as b approaches infinity. Natural log x plus 1, sorry, I should cross that out, not the ln. Natural log x plus 1 minus natural log x plus 3 is natural log of x plus 1 over x plus 3. That is from 0 to b. Okay. So let's plug these in. So we have, let's see here, limit as b approaches infinity. Ln of b plus 1 over b plus 3 minus ln of 1/3. Okay. So as x or b goes to infinity, b plus 1 over b plus 3, those are both linear functions, and so we just look at the leading coefficients. It's 1 over 1. That's natural log of 1, which is 0. So this goes away. Oh, come on. So this goes away. So we just have negative natural log of 1/3. Could put the negative to the top. That is natural log of 3. Whew. Lots of work for that one, right? Awesome. All right, let's try this one. Looks like an integration by parts situation because we have an x times an e to the negative x. Let's make a table real quick. U dv, x, 1 and 0, e to the negative x, negative e to the negative x, and then positive e to the negative x. And so now, let's see, we have our arrows, positive, negative. So our antiderivative going to be negative x e to the negative x minus e to the negative x. And we do this from 1 to b, limit as b approaches infinity. So all those limits just make the infinity a b value, and b is approaching infinity. Okay, so if we plug in b, let's do it over here. So limit as b approaches infinity. It'll be, let's see, plug in b here, we have negative b, e to the negative b, and write that as over e to the b. And then minus 1 over e to the b. That's what we get from the b. And then we subtract from that when we plug in the 1. So we'll have negative e to the negative 1, that's negative 1 over e, minus 1 over e again. Okay, so this first part here, as b approaches infinity, that is a L'Hopital, right? We have infinity over infinity. Take the derivative, you have negative 1 over e to the b, which as b goes to infinity turns into 0. And 1 over e to the b, 0 again. So then we have, let's see here, positive 1 over e and positive another 1 over e, so we have 2 over e. All right. So this one, I'm not sure what that graph would look like. You could graph it on Desmos if you wanted to, and you could see that if you integrate from 1 to infinity, it's probably going to, I would guess this function does something like this or something, I don't know. But from 1 to infinity, it's going to get super small over there to the right. Eventually, you're not adding enough area for it to matter at all. All right, so this is kind of to drive a point home that we're going to talk about more in Chapter 9, but this is x to the negative 2. So the antiderivative will be negative x to the negative 1, or negative 1 over x. This is x to the negative 3, so you add 1 to that, you get a negative 2, and divide by the same thing. It's going to be negative 1 over 2x squared, I believe. Or is the 2 on the top? Nope, it's on the bottom, I believe. Yeah, because it would be negative, sorry. Didn't think about this. X to the negative 3, add 1, x to the negative 2, divided by the same thing, negative 2. Yes, that's what it's going to be. Okay. All right. Now, over here, 1 over x is unique, right? The antiderivative is natural log absolute x from 1 to infinity. They'll all be positive, so I don't have to worry about the absolute values. Now let's see what happens when I do the limits for each one of these. So you'll have a limit as b approaches infinity. It'll be negative 1 over x. From 1 to infinity. We actually did this one in the bell work. Plug in infinity, you get 0. Oops, I actually shouldn't have an infinity there. It should be a b. There we go. So we have limit as b approaches infinity of negative 1 over b minus a negative 1 over 1. This turns into 0. 1 over 1 is a positive 1. Here, let's see here. We would have limit as b approaches infinity of, let's see, it would be negative 1 over 2x squared, 1 to b. Plug in b to infinity, negative 1 over 2b squared, and then minus 1 over 2 times 1 squared, which is negative 1/2. It's minus a negative, so it's going to become a positive. So this goes to 0, so this becomes a positive 1/2. This guy over here, though, is interesting, right? We have natural log x. We have limit as b approaches infinity. It'll be natural log of x from 1 to b. Plug in b, so we have natural log of b minus natural log of 1. Natural log of 1 is 0, but natural log of infinity approaches infinity. So this actually diverges. And this gets to an important point, that x squared, x cubed, these graphs get very close to 0 very quickly, because that square is going to make the bottom of the fraction big really fast. And as long as that exponent is above 1, even try it on your own with 1 over root x, integrate it from 1 to infinity, you'll find the same thing. It's okay there, but if it's just 1, it's actually not going to work. And actually, I take back that, what I just said. I think if it's 1 or less, so like in this case, I don't think it will work. But give it a shot, see what happens. But there's kind of a hard and fast rule where if you have 1 over x to the n, if n is bigger than 1, you're okay. If it's less than 1, it's no good. That's kind of the idea. All right, so now I want to go through a famous problem. This is definitely not a problem that you need to know. It's very easy to do, and you guys all have the ability to do it. It's kind of cool, so follow along with me and let's see what happens. There is a structure called Gabriel's horn. Gabriel's horn is created by taking the function 1 over x, which we just talked a little bit about, and you revolve it around the x-axis. Okay, so 1 over x revolved around the x-axis would look something like this over here, right? And at the bottom here, that would be negative 1 over x, right? That's the bottom function. But you have this revolved around, so it's going to create disks, right? And we can find the volume of this thing. Usually you start it at 1. Okay, so if you started at 1, then this beginning part isn't going to matter. The reason it's called Gabriel's horn, it goes on forever over here, but it would kind of create this kind of like trumpet bell looking thing, right? It'd be like the bell of an instrument. So the question, of course, is what is the volume? Okay, so the volume of Gabriel's horn would be the integral from 1 to infinity, start at 1 here, pi times the radius squared. So pi is on the outside. The radius of that disk is going to be the height of the function, so it's 1 over x whole thing squared dx. So that would be the pi times the limit as b approaches infinity. Antiderivative of 1 over x squared. So that is x to the negative 2. Antiderivative negative x to the negative 1. We've seen that lots today already. So we're going to have negative 1 over x from 1 to b. So we plug in b. Let's see, we have pi limit as b approaches infinity, negative 1 over b minus a negative 1 over 1. This is 0. This is positive 1, so we have pi times 1, which is pi. How crazy is that? We have a revolved, infinitely long volume, and it ends up having a total volume of pi. Now, where it really comes into to be interesting is if you find, they call this the shadow cast by the horn. So if we want to find just the area, right? The volume gave us a value of pi, but what if we wanted to find the shadow that's cast by the horn? So to find the area here, we're just going to integrate from 1 to infinity. the distance between here. So this is 1 over x, or this is negative 1 over x. So we do top minus bottom function, 1 over x minus negative 1 over x dx. So that is the limit as b approaches infinity, integral from 1 to b of 2 over x. Right, because we have two of them, 2 times 1 over x dx. Now we just did this, and we actually showed that this is divergent, right? This is going to be 2 times the limit as b approaches infinity. Just pull the 2 out to the front. 1 over x, so the antiderivative of that is natural log. I'm just going to do an x because we're all positive numbers, so not to worry about the absolute values from 1 to b. Oh, too far. And now if we plug in the b, we have 2 limit as b approaches infinity, natural log of b minus natural log of 1. Natural log of 1 is 0. Natural log of infinity is infinity. This diverges. Now let's wrap our head around this for a second. We just showed that the volume is pi. So it has a finite volume. The volume from 1 to infinity will never go above pi. But the area that it casts with its shadow is infinite. So what this means, the way they sometimes say it, is you could fill it with paint, but you couldn't paint it. You could fill it with paint, but you couldn't paint it, because the area of it is infinite, but the volume of it is finite. Gabriel's horn. Kind of a cool little way to end this lesson. Love you guys. That's why I'm here. Have an excellent day.